Welcome to The Explainer. Today we're diving into what is arguably one of the most counterintuitive and frankly fascinating discoveries in all of modern cosmology. We are looking at a phenomenon that completely redefines how we measure the sheer vastness of the cosmos, and we're doing it using something you would probably never ever expect to find in the vacuum of space.
So, we all know the famous rule, right? Space is a vacuum. Sound can't travel through it. You can't hear anything in space. But asking if we can hear the early universe, that completely upends the whole assumption. Because as it turns out, cosmologists actually do have ways of hearing the sound of the universe. They do this by reading these incredibly ancient echoes left behind from the very beginning of time itself.
All right, part 1, the early universe's symphony, the primordial plasma. Let's journey back nearly 14 billion years to when the cosmos was a very, very different place.
Okay, to really grasp this, we have to tackle this incredibly ungainly term, Baryon Acoustic Oscillations, or BAO for short. I know, it sounds like a total mouthful, but let's break it down. Baryons are really just normal matter. We're talking about the protons and neutrons that make up you, me, the Earth, the stars, the whole shebang. And in the early universe, these acoustic oscillations were essentially just giant cosmic sound waves, literally rippling through the dense fabric of space.
Here's how it actually worked. Before atoms even existed, the young universe was this incredibly hot, dense sea of charged particles and light, basically a glowing, nearly perfect plasma. But there were these tiny quantum fluctuations left over from the Big Bang that created very slight differences in density. So gravity starts doing its thing, constantly pulling dark matter and normal baryonic matter inward toward those slightly denser spots. But as that matter compressed, the radiation pressure from the photons, the light, became incredibly intense, and it aggressively pushed the matter back outward. This constant seesawing tug-of-war between the inward pull of gravity and the outward push of radiation acted exactly like dropping a pebble into a calm pond. It created perfectly spherical sound waves that just propagated outward through this primordial soup.
And when you look at the actual physics here, it reveals something completely mind-blowing about the conditions of the universe back then. Because the photons were providing almost all of the outward pressure in this tightly coupled plasma, these were definitely not your ordinary sound waves. Driven by the sheer, literal force of light, these waves raced outward at over half the speed of light. We're talking roughly 170,000 kilometers per second, just incredibly fast.
Moving on to part 2, freezing the cosmic ripples, the recombination epoch. Let's see what happens as the rapidly expanding universe finally starts to cool down. So from the exact moment of the Big Bang at T0, these massive sound waves are just expanding outward at those ridiculous speeds, and they do this for hundreds of thousands of years. But then, right around the 380,000 year mark, the expanding universe finally cools below 3,000 Kelvin. And that specific temperature drop, it crossed a critical threshold that changed the laws of cosmic physics forever. What happened next was just dramatic. As the universe cooled down enough, electrons and protons could finally bind together to form neutral hydrogen atoms. And because of that, the free-roaming electrons vanished, meaning the universe instantly became transparent. Light could finally fly free. In fact, that light became what we now observe today as the cosmic microwave background. But here's the kicker. With those photons gone, the outward radiation pressure that was driving the sound waves, it vanished, instantly. This completely stalled out the sound waves. It literally permanently froze these expanding spherical shells of matter exactly mid-stride.
Which brings us perfectly to part 3, the ultimate standard ruler, a cosmic measuring stick. This is where those ancient frozen ripples become absolutely crucial for modern astronomy. You see, to measure the vast distances of the universe, astronomers have traditionally relied on something called standard candles. These are objects of a known intrinsic brightness, like a Type 1a supernova, and you use them to gauge distance simply by looking at how dim they appear from Earth. It's pretty straightforward. The dimmer they look, the farther away they must be. But Baryon Acoustic Oscillations, they give us an entirely different toolkit. They give us a standard ruler. This lets us measure distance by observing how large a known physical shape appears from incredibly far away.
Because these specific sound waves expanded for a very specific amount of time, at a known speed, before they suddenly stalled out, they left behind a fixed, co-moving scale. Now, a co-moving scale is basically just the foundational measurement that stretches exactly as the universe itself expands. Over the last 14 billion years, that exact scale has stretched alongside the cosmos, and today, it measures roughly 150 megaparsecs, or a whopping 500 million light-years across.
So why does this 500 million light-year number matter?
Well, over billions of years, gravity went to work on these frozen ripples. Dark matter had mostly stayed near the center where the sound waves originally started, but the frozen baryon shells on the outside provided this massive dense outer ring of extra gravity. Gradually, cosmic gas pooled into these high-density edges, which sparked the birth of countless stars and galaxies. Because of this incredibly structured formation, if we look out at the universe today, we statistically expect to find an excess of galaxy pairs separated by exactly that massive 500 million light-year distance.
Okay, Part 4, Mapping the Ancient Echoes, Reading the Galaxy Surveys. How in the world do we actually see these faint, invisible, ancient ripples in the modern universe? Well, it takes a staggering amount of data.
By meticulously mapping out millions of galaxies, these incredible astronomical surveys, like SDSS, made the absolute first definitive detection of this separation signal back in 2005. Then projects like BOSS came along and mapped higher redshifts, which just means they looked much further back in time, expanding our precision. And most recently, the 2024 DZ project mapped 6 million galaxies, along with these hyperluminous objects called quasars, proving this preferred galaxy separation scale with staggering sub-percent precision. It's just wild what they can do now.
Which leads us to Part 5, Dark Energy and Cosmic Destiny, Charting Expansion. Let's dive into why mapping these exact echoes is one of the most important endeavors in all of modern physics.
By observing how the apparent size of our 500 million light-year standard ruler changes at different distances, cosmologists can precisely track the expansion rate of the universe over billions of years. It acts as this brilliant, completely independent way to chart how dark energy has accelerated cosmic expansion. It is quite literally a critical test for all of our cosmological models.
And what is truly thrilling about this, and honestly why this is making major headlines right now, is that the recent DESI measurements suggest a slight tension with our standard models. The data is hinting that dark energy might actually be evolving. It might be changing over time, rather than just acting as a static, unchanging cosmological constant. If that's confirmed, wow, that shifts our entire understanding of cosmic physics. It's a real game changer.
It's profoundly awe-inspiring when you stop and realize what we are truly looking at here. We are mapping the cosmos, and we are uncovering the deepest mysteries of dark energy, using what astronomers literally call frozen sound from the beginning of time, imprinted into the deepest reaches of the sky.
As our galaxy surveys grow ever more precise, looking deeper into space and further back in time, we really have to ask, what will these primordial sound waves finally teach us about how our universe will ultimately end? Is dark energy going to tear everything apart, or is it changing its mind? It's an incredible mystery, and we are actively solving it today. Thanks so much for joining me on this explainer, and as always, keep looking up.